So I hope this kind of gets you motivated about why the study of fluid mechanics is such an important subject. Questions? Okay. So let's touch on the homework. This is the last homework on dimensional analysis by way of similitude. So you're given a problem where a sphere is put inside a pipe. So it's an internal flow, and the drag we're told as a given a function of the four parameters on the right-hand side, where the two diameters is that of the sphere and of the pipe itself. And you're given a set of data from a model testing, and you're asked to extrapolate what the prototype will behave. Those details you can read in the problem statement, but I want to ask you two questions. One is, what assumption is this problem making? Second, to do the similitude, you have to formulate some pi terms. Which three independent variables will you pick to form those pi terms? So let me just start with the first question. Problem like this, very standard. Immediately by inspection, tell me what assumption is made by this problem. Implicit. How do you know? How do you know? Because on the right-hand side, there's no viscosity as told by the problem statement. So there will be no Reynolds number. Do you see that? Okay? So second question is, what three terms on the right will I need to take to form those pi terms? So let me give you just some consideration. A, B. Think about which one you will choose. I won't tell you the answer. If you don't know it now, you're a little behind. Okay? I'll leave it at that. Only either A or B acceptable. You have to decide which one. Questions? That's it. That's all I want to give you in way, by way of the hints on the homework. And then that's more than sufficient. Okay, so we're done with dimensional analysis. Any question I can answer before we leave that behind and move on to a new chapter? Are you all square with the use of the pi term, pi theorem, sorry, how to formulate the pi term, how to match model versus prototype, etc., etc.? Yes?
The homework from last week, you can do it by inspection, it's fine.
So for those in the back, question is, all the homework moving forward, as well as problem in test 2, can you formulate the pi term by inspection? Or what do you think the answer is?
Yes.
Yes, as long as you do it right. Yep, so it's fully acceptable if you get the right answer. And how do you know your answer is right? Unit, you check it. You check it. You plug in all the unit for all the terms. If they come up with dimensionless, then you've done it right. Right? If you're not comfortable, a new problem that you've never seen before, you're clueless as to how to start, then go back to the lengthy method with the 3 equation and 3 unknown. Right? So it's just that straightforward for forming the pi term. The only place you can get caught, remember what I said about dancing, you start with 1 foot, everything go downhill. If your dimensionless, if your fundamental primary units, the mass, length, and time is incorrect for any of the quantity, pressure, viscosity, then there's no way you can get the correct pi term. So that's the only place you may make a mistake. Make sure it doesn't happen. Right? Okay. Any other question on dimensional analysis? Do you see how fit in the whole big picture of the curriculum of fluid, that we have done a lot of control volume analysis, very simple back of envelope calculation, good to 5–10% accuracy. We see a little bit of differential analysis, and we'll spend more time on it, but this whole chapter on dimensional analysis, chapter 7, is about experimentation, which is always needed. I don't care what simulation you do on what computer and how expensive it is, you always go back to an experiment. First in a model and then a prototype. And that's how things are built. Okay, very good. Changing gear. So last time I gave you a lot of introduction of this chapter in so-called internal flow, what I mean by internal versus external flow, and for pipe, where Reynolds number is less than, and this is not a magic number, this range anything from 1,000 to 4,000, but for our academic homework type purpose, we kind of choose 2,300. And that the two Virgins, it's a very peculiar word, Virgin R, or loosely translated, two characteristics of this pipe flow, all determined by the value of the Reynolds number. The lower end, lamina, is characterized by one word, and the higher Reynolds number, which is greater than 2,300, is also very simplistically characterized by one word. So someone tell me for the lamina, lamin, what that one word is. I didn't finish this in my lecture last time, but it's something you have seen from your 21-24 when I have a water tank with very little water on the left, meaning that the gravity-driven flow for the pipe exiting to the right is a relatively low velocity, 1 meter per second. And I insert the needle to the flow, and I introduce some dye, some wet dye. What will happen to this dye as it carries with the fluid from left to right? And hence the word lamina. Anyone remember?
Streamline?
It stays with one filament, one ribbon. If you release the dye in the center, it stays in the center. It doesn't disperse, it doesn't mix. So what is one word that is most appropriate to describe this so-called laminar flow where the velocity is very, very low, 10 feet per second? And you will find out by example in homework how low is low. What's one word? Steady. That's pretty good, but I may want something more descriptive than just steady. It is steady. That's just a fair answer. But I want something even more descriptive than that. Yes?
Linear?
Linear. Not quite, but it does sound like letter L. It's letter L.
Layer.
Layer. Thank you. Layers. Why? Because each of those filament is not talking with the adjacent filament. It's just they don't exist relative to each other. I don't see you, you don't see me, don't disturb me. So they behave like a filament or layer. And the dye stay where it is, never mixes the whole tube. Right. Have you seen that in 21-24? Yes, no? Or you forgot? So please read it as a review. Now if I fill the tank to a higher level, to the top, what change? You have done this problem many times in chapter 3. So what changed when I fill the top? We fill the water at the top of the tank.
Pressure.
What?
More pressure.
More pressure and then what? more velocity in the pipe, right? It's all gravity driven. H from what you can draw that conclusion? From what equation you can tell me that the velocity due to this higher column of water has resulted in faster flow in the pipe? Bernoulli, thank you. Bernoulli, yes. Do you see the pieces, how it fit together? So a higher velocity, same experiment. A needle, a smoke generator, or anything that can identify the motion of the fluid. You know, without that, they're invisible. You can't see what's going on. But if you put some color in it, put some smoke in a wind tunnel, you can track the flow. What will happen to this dye? It completely mixes and fill the entire exit pipe with red color, almost instant. Okay? There's so much small-scale unsteadiness. Imagine the water molecule is dancing, shaking hands, going up and down from the center to the outer wall and so on. That it completely mixes. That's what we call turbulent. The country is in turbulence. Is it good or bad? What is the equivalent word that will best describe turbulence? Chaos. Chaotic. No good. Just no rule, no regulation. Everything is just in a state of chaos. Yes?
So if we have like a nozzle, then you go from, you know, like a lower velocity to a higher velocity. So that means you're going to somehow, somewhere kind of switch between
Yeah.
laminar flow and turbulent
Yes.
flow. So what, does the turbulent flow like interrupt the laminar flow and kind of like work its way back and kind of like screw it up?
It's a very complex problem when you go in a flow field like what you described, that the velocity is changing. Yes, indeed. It's called transition. So we, in a very introductory level like this, just make things very transparent and simple. Black and white, laminar, turbulent. In real life, it's very gray. So there's a region that transition occur. And people at Boeing spend millions and billions of dollars to study that. When does it occur on the wingspan? When the flow accelerated from low speed to high speed. A Pratt & Whitney or GE aircraft engine on the turbine blade, the flow go from 0 meter per second at the stagnation point to Mach 2 at the exit of the turbine. They go through low speed to high speed. Where does this transition occur? By now, it's still a black art. That's why they hire you to do analysis. Okay? This is but a very, very simple-minded representation of a very complex problem. Right? This is internal flow. Why that's described as more like external flow, like on a wing. But what you're asking is precisely why they need to hire you, even after building aircraft engine for 40 years. Because it's still an art. Okay? It's a long answer to a very short question. But all those are jobs. Model testing, there's a lot of pitfall, because despite computer that can calculate to the decimal of 20 figures, garbage in, garbage out. All right? And testing is not perfect. So you have all this information as a high-level manager, and you make a decision as an engineer. That's what you get paid for. And you just hope that you're right. And you're not always right. And then you fix it. And it's very expensive. Okay? And that's opportunity for us. Okay, so this is just the backdrop of review of 2124. We'll build on this, and we'll look at how it leads to a Moody diagram, and how we may then do analysis of the pipe once I have introduced the energy equation. But before that, just a very quick drop on the homework, which is a relatively simple problem, flow in a pipe of air, but at 200 degrees Fahrenheit, so it's a little different than what you're accustomed to in room temperature. So what is needed if the air is heated? So the problem asks you, what diameter is needed in the pipe to keep it from a laminar flow. And the problem also gives you a flow rate, which is very peculiar. This is exactly how it's given in the problem statement. So the two question is, what does that mean? 0.08 pound per second. Until you can interpret that, you cannot do the problem. Number two, what does it mean when the air is warm, heated, 200 degrees as opposed to room temperature? So what? So first question, anyone have seen this before? A unit of flow given in something of lb per second? What does that stand for, lb? Pound mass or pound force or what? Pound force, very good, at least you remember that. Have you seen a unit of flow given in pound force per second before? Ever? When? You don't remember. Never. Have you had a problem that you've actually been given a flow in pound force per second? Yes?
Wasn't that wide pipe example in the beginning of the semester?
Is a what?
The wide pipe where I had the two inlets and one outlet?
You're close. I was about to bet you lunch that you will not remember. So you remember half of it. You get half the lunch. It was the problem, but it's not a true inlet problem. It's a circular lubricating oil problem that we did by way of continuity. So if you forgot, go back and look at it. Okay? That's the only hint I give you because it's been covered before. And that's how you deal with what's called a weight flow. Not a mass flow, not a water flow rate, but weight flow given in pound force per second. Okay, one more introductory comment before we launch into the energy equation. So for entire chapter 8 of pipe flow, internal, because it's wall bounded, we have to make another further distinction of an entrance region, which is in the beginning of the plumbing, beginning of the pipe. Like the pipe fed from the water tank to your kitchen faucet. So we have a distinction called entrance beginning region, which behave a little differently. And if I go much, much further downstream, so those are the pipe wall, circular. And most of chapter 8 will be circular pipe flow, except at the very end where we deal with some particular ducting for air conditioning. So the difference is this, the entrance region versus what we call a fully developed, meaning it's no longer changing region of the pipe or vagine. Vagine, I didn't mention it, is the same word as characteristic. So the Reynolds number of small lamina is one full vagine, or one full characteristic. So here the entrance region, just to remind you, there's no slip condition that we have barely touched on more than one occasion. Before they enter this bell mouth, the flow is uniform with a velocity that is constant. Once I'm inside the pipe with the presence of the wall, I have the effect of the viscosity at the wall, resulting in no slip condition on the perimeter of this circular pipe. Where right at the wall, what is the velocity? 0. We call it the no slip condition. Due to viscosity, friction. tells you right at the wall, the fluid is not moving anywhere because the wall is not moving. So as a result, I have a velocity profile that is no longer uniform. And the region where the flow is not uniform is that outside the dash line. That flow within the dash line, inside the dash line, we call it a boundary near the wall. Boundary layer is description of something relatively thin. And it's developed because of the effect of viscosity. So that's the concept of the boundary layer, and as a result of low slip condition. Outside of that, where the effect of the boundary layer is not felt, we call the inviscid core. Meaning, in the center of this pipe, you don't feel the effect of friction yet. So it's behave as though you can pretend that there's no friction. We call it inviscid. Frictionless. Core meaning in the center. Okay? Any question on this concept? It's the first time we kind of formally talk about the effect of viscosity on the wall and formulating a boundary layer, and that is very fundamental to viscous flow. We will revisit this later on much more vigorously by looking at the equation of motion with friction inside the boundary layer. It's called the Navier-Stokes equation, which is the cousin of the Euler's equation, now adding the viscosity to the couple. Question on this? However, if the pipe go on continuously for, say, a couple of miles, eventually, what happened to that dash line? As the boundary layer continue to grow, and the effect of friction continue to move inward towards the center line. They finally meet. Keep going, they finally meet in the center. And at that point, we call it a fully developed, meaning no longer is the velocity profile changing. You will have now a velocity profile, which you have seen in some of the homework. In some cases, it's parabolic.